Here, I can, okay, I'll put them on. It's okay, I just look like a big blob, you know, black blob in front of a screen. It's okay. No, I don't care. I completely don't care. Okay, so me-theory provide the solutions, and you guys have that document with you. And we're talking about interaction with a homogeneous sphere. If you want more advanced codes that do non-homogeneous or non-spheres, they exist, but they're not me-theory, and this is a nice way to get into what these codes provide you. And we're also going to play a little bit with the anomalous diffraction approximation, which is the one you have the Excel spreadsheet for, but they have some MATLAB code for it. So the inputs, as we said before, are the wave of light in the medium, the index of refraction of the medium, the index of refraction of the particle, again, relative to the medium or relative to air if everything is done relative to air. And as we said, the n prime, which is the absorption, the imaginary part of the index of refraction, which really has to do with the absorption in solution of a normalized such that it has no units by the wavelength. What else? And then we can calculate extinction, coefficients, and efficiency factor. This is what's going to come out. I covered all these before, so I don't have to go through it now. So now let's just do some games. And in the appendix here and in the spreadsheet, I have all the approximations that I could find to date. Okay, so let's assume we have a phytoplankton. It has an index of refraction of, so it's near an absorption band at 440 nanometer. So we're right at the blue peak of absorption of a phytoplankton. So I have my absorption peak. I'm looking right here at 440 nanometer. And let's assume at this wavelength, the phytoplankton is 1.05 plus the imaginary number 0.01. Okay, that's usually, I mean, that's the kind of order of magnitude you get. I'd love to if I could find something different. All the white ones are tiny, but here, I found something a bit bigger. Okay, let's see. You just have to change one every 2 minutes. Okay, 0.1 times I. What's it? D equal 2 micron. So diameter is 2 micron. And lambda is 440. And we can ask ourselves what analytical regime is applicable for such a cell. So I'm going to go to the end here. And I'm going to have to calculate all these things and see what the values are. So, because as you see, the analytical regime, for what they apply, it has to do with x. X is my size parameter, and x is further up. It's pi d over lambda. Now this is lambda in the medium. So lambda in the medium is actually this will be equal pi, 2 for diameter, divided by 440. Now I have to be careful. This is in micron, so this has to be 0.44 times divided by, 1.34. This is how we convert to wavelength in the. So can somebody tell me what this value is? What is x? Because I need this to decide. So this is the size parameter. This is this size parameter. 19. Okay, 19 is Rayleigh regime required to be much smaller than 1. Doesn't work. It's not a Rayleigh particle. Now this one requires something about m, which is okay. It's very close to 1 because 1.05 and this is 0.01. But rho, I don't know what rho is, so let's do rho. Rho equals, this is my van der Waals parameter. I call it, some people call it, is 2x times n minus 1. 2x times n minus 1. N minus 1, this is 0.05. 2x is 2 times 20 will do, just easier instead of 19. This is 40. 40 times 0.05 equals, I think it's equal to 2, doesn't it?
Yeah.
2. Okay. So I'm at 2, about 2. Okay. So Rayleigh-Gans-Debye require rho to be much smaller than 1. 2 is not much smaller than 1. Hosed with this one. But, lucky me, the van der Halst, I'm dealing with relatively large particle. X is 19. Fine. This is correct. It's close to 1. And rho can be bigger than 1. Ah! This is van der Halst. As I told you, this is what we use, or anomalous diffraction. Excellent. So now let's see what we're supposed to do with that information. Going back up. Okay, so now, based on this approximation, what is the attenuation, scattering, and absorption per cell? So I have one cell. I have one cell in a meter cube. What is A, B, and C? Actually, this you can do in your Excel spreadsheet. It's exactly what Colin did with us before. And let's assume now that we have 5 times 10 to the 4th per ml. What is my A, B, and C? So we have a small code to do it. First we'll do it with the anomalous diffraction. So do it in the Excel spreadsheet. First do this in the Excel spreadsheet. Tell me what you got, and then we'll do it with the full me code. Okay, so can somebody do it on the Excel spreadsheet? Put this value in and tell me what you're getting for one cell, and then what you're getting for 5 times 10 to the 4th cell per ml. So remember, you have to change this for cells per meter cubed. How many ml per meter cubed? There's 1,000 in a liter, and then another 1,000 liter in a meter cubed. So that's 10 to the 6. You have to multiply this by 10 to the 6. So this is 5 times 10 to the 10th cell per meter cubed. Okay, so can somebody tell me, this is basically your Q times cross section here. This will be your Q times, these are the big C's. Q times cross section, so pi d square over 4. But this is right in Colin's write-up. You can do it in the first page of the Excel spreadsheet. Okay, let's see you guys being able to input numbers into that spreadsheet and tell me what you get. So we're going to do the van der Halst, and then we'll compare it with the me code. And this will put me. And here we'll have A, here we'll have B, here we'll have C. And this is for the full population, for all this monospecific. Yes?
We're using this relative to N for water, or is it
In our code, it's automatically, there's no relative, the wavelength has to be in water.
I meant the N relative to water.
The M is already relative to water here.
That's relative to water.
That's relative to water. If in our code, then you multiply it by this one by 1.34.
Okay.
If in our code it's in air, you have to multiply it by 1.34. Just the real part. Please don't. Okay, so use the Excel spreadsheet. We also have an M file for that, but it's easier with Excel for most of you. So let's see what you're getting. Ask if you're stuck. If there's something that doesn't work for you, please ask. The culture is getting desiccated at this rate. Two micron diameter. How do you know that you're more than what it should be?
Just because even our row is different by a factor of 10.
By a factor of 10?
Yeah. So somewhere a factor.
So here we're wrong? Pi, there's a pi here that may be pi times d. So pi times 2 divided by 0.44
That's what I did in MATLAB
to get the size parameter. And it doesn't fit the size parameter that...
Not
Well, every size parameter is rho. It's not that. The rho is 2.
Yeah, it calculates rho, and it gives 1.9.
Because, oh. Maybe I did it wrong. It calculates rho and it gets 1.9? What? So that's for rho. That's okay. I got 2. So the rho is correct. Okay, so you have an A. So Ben, come on. Tell me your A. Yeah. I want an A, a B, and a C. Or somebody else here.
RA 0.11 for A. Yeah.
How much?
0.11 for A.
0.11 inverse meter for A. 1.49 for B. 1.6 for... Is everybody okay with those values? What? You got something similar? No. You can't. Why can't you get anything? Remember, the M you should multiply by 1.34 because she's putting it in air in her code.
But we only change the red parts.
1.05 times 1.34, the wavelength is 440 nanometer in air, or 0.44 micron. Do you have that? Did you change that? You're good? Okay, they're good. Anybody? What? What did you get? No, the number of particle we have is 5 times 10 to the 10th cell per meter cube.
No, I'm just talking about the M particle.
The M of the particle is 1.05 times 1.34, and that's 0.01 for n prime. 0.01 for n prime. Do you see an n prime there? Yes, it's the relative.
This is just N prime here, but N prime is not here.
That's fine. Here it is, this one.
Oh, the N?
N prime, yes.
Oh,
So change that to 0.01. 0.01. You're good?
0.
Excellent. Yep.
Then what got different to say?
Then you need, the particle diameter is 2.
Yeah.
This is correct. Wavelength in water, that's fine. The number of particle. So this is correct, but now you have to multiply. These are the Q's.
Okay.
These are only the Q's. So let's put the Q's, and then you have to multiply the Q's by the cross section and by the number of particles. Okay? The cross section, but remember, the cross section is going to be pi times 2 times 10 to the minus 6, all this square divided by 4. Awesome. So that's the cross section, and then you have to multiply it by the number of particles. Liza, are we online?
I'm trying to calculate it now.
You multiply those Q's that you got from Collins code by the cross section. So that's pi 2 times 10 to the minus 6, because it's a micron, square, all that 2 to the minus 6 square, divided by 4. In order to get in meter squares. And then by the concentration, 5 10 to the 10 particle per meter cube. You're good? If you're not here, we're going to wait until everybody's here.
Those are going to change.
What? Those may change? Those are going to change? Uh-oh. No, I'm asking them for A, B, and C, not the Q's. I mean, the Q's should be, we can do the Q's just to get a sense of what the Q's are. Let's do the Q's as well. Okay, let's do Q's. These are IOPs, and let's do Q's. QA, we'll have QA here, QB here, and QC below. And this will be for the VDH. And this will be for me. Okay, what Q's did you get? 1.12 for QC. For QB? 0.31. For A, 0.31. And for B? 8.1. So Q's 0.31, 0.81, 1.12. Yeah? You didn't get those Q's. Oh. Let's look at what you have. So 0.01, that's correct.
You have to change your air.
2 is correct.
Your water wavelength.
Wavelength, what's your wavelength? 440, that's correct.
I don't know, 1.447. What did I do wrong?
So you have to multiply the m of the particle. Is this 1.05 times 10 to the, this should be
It's 1.5 times 1.
34. That's okay. That's okay. The diameter is 2.
Yes.
Sorry.
40.
0.01 is correct.
Yes.
This is correct. So you should get 1.54. Yeah, so people are getting other values than you guys.
Because you change your air to so you make sure you're.
Yeah, 1.05 times 1.34. That's one. That should be 1.0. It's 1.047. 1.47. Sorry. So this is 1.4707. 1.407. That's the real part relative to air. Okay. 440 nanometer.
Yeah, but see, their wavelength in water is not, their wavelength in air is 440, not the wavelength in water.
That's the wavelength in air. You always report in air. So you guys are, you're wrong. Okay, so now let's, we never know what is in water. So let's correct it. So let's tell me. What? We know, but that's never what we talk about. When we talk about an absorption curve, it's always the values in air that we talk about.
Change the air to 440 then.
Yeah, air is 440. And we did. Here is when we transformed it to be what it should be in water. When we calculate, we divide it by the index of refraction. So these are going to change. So let's, can you tell me, Ivana, what you got for QA?
QA is 0.389.
0.39, okay. QB?
1.15.
1.15. And together, yeah.
1.54.
1.54. Okay. Is this more consistent? 0.39, 1.15, 1.54. Okay. So what does that translate to in terms of A, B, and C?
I got 0.062.
0.086.
Yeah, 0.19.
0.19 in B?
Yeah,
And for C?
I got 0.25.
That cannot be. Because A plus B equals C. So, Ivana, you did you?
0.06.
Where? In 8.06. Okay. 0.25 for C. No. Now we're going to run. We didn't run me code yet. That's okay. We'll get there in a second. But did everybody calculate that?
Where did you say how many cells in ml?
The cells are 5 times 10 to the 4th per ml. So then it's 5 times 10 to the 10th per meter cubed, which is what you need to multiply by. And this also has to multiply the cross-section area, which is pi times d squared, where diameter is 2 microns, so 2 10 to the minus 6, squared divided by 4. Are you there? You're done? Or not?
Not quite close, but yeah.
Because you were done in one point. Did we perturb your world?
Now it seems like I'm getting it wrong by a little bit.
Well, by a little bit is fine. As long as it's, you know, the
General ballpark.
Not at all. Did you get these Q's? The Q's are good. So now multiply them. Take the Q's. Multiply first by pi times open brackets. 2 times 10 to the minus 6. 2 e to the minus 6. Close brackets.
Minus 6.
10 to the minus 6. To the power of minus 6. Close brackets. All that squared. All that squared. Divided by 4. So that's the cross section. And all that, so that will be for 1 particle per meter cubed. But you don't have 1 particle, you have 5 times 10 to the 10th. So multiply all that by 5 times 10 to the 10th. Times 5, e to the 10. Just do e. Don't do 10. You can use e. 5 times 10 to the 10th you can write 5 e 10.
Rounding a bit off. 0.18.24. So B is 0.18.
I tell you, Jason, I can't trust you anymore. Five e to the 10th, 10 to the 10th cells per meter cubed. Okay, you got something reasonable? Awesome. Anybody else is struggling? You good there? Awesome. You good? You good over here? You're good. You good? Quentin will help you. Yes? Okay. Awesome. Guys, everybody's on? Everybody's good? Did it work for you? You're not? Didn't work for you yet? Did you get these cues? This is good. Did you get this? No. So in order to go from here to here, you multiply from here to here. You multiply by pi d squared over 4. Okay? D squared, but you write this as micron. So 10 times 10 to the minus 6 square. Okay? And then you multiply by the number of particles. And the number of particles per meter cube is 5 times 10 to the 10th. You're good. Awesome. Everybody's good? Jordan? You're good? You're getting there or you're good? Because I want to move on, but I don't want to move on before everybody's on board. Yes?
You got the same answer but different from that one. I just wish which one with that slide. I mean this for the that here is like this is like the
Yeah, that's okay. That's all good.
why would you have like
That's okay.
QA with different with the one?
Okay, your QA is 0.38.
Yeah.
So 0.38. It's the same. It's the same. The QAs are same. But did you get the same C, A, B, and C?
Not yet. I just followed
This is fine. So now you have to multiply these by the number of particles and by pi d squared over 4. Jordan, you good? Multiply by n.
Yeah, is the power of 10.
You multiply by the cross-section area, which is pi diameter square, 2 10 to the minus 6, all this square, divided by 4, times n. Yeah.
Quick question. So
Yes.
for n particles, you enter 1.05 or 1.05 multiplied by 1.34?
Depending what your code asks. If it asks the value in air, you multiply by 1.34. If it has the value in water, you use the 1.05. So it depends if it already does it in the medium or not.
Okay, so in the case of the Excel sheet, it's 1.05.
No, in Excel sheet it's 1.407.
Then that's wrong.
Well, it should be there. You know, it says in air. If you look at the Excel spreadsheet,
This is in water.
this is in water. That's okay. But you start here. You put it here as 1.47.
Okay.
407. Sorry, 401 is okay. That's okay. So you're good. You're good.
Okay.
That's fine.
And then this is
Yeah.
okay.
So then you get the right QA, QB, and then you have to calculate A, B, and C. Are we on? Everybody's good? So 0.06 for A, 0.18 for B, 0.24 for C, or something. Good. Awesome. And you know how you do it for one and you copy paste below. You don't have to write it, type it for each one of them. You got it? Awesome. Lisveta, you on? Awesome. Okay, so now comes the cool part. Now we're going to do it with the full me code, just to see how well this approximation works. So we go to MATLAB. I mean, we go to wherever we have that. MATLAB is open for me, and I have the one called callbh.m, which I'm going to open, but I'm not opening in. Is it? No, it's not opening in the right. Sorry, I have to open it within MATLAB. I'll do that. Ah, okay. Let me change my directory to the right directory. What? Callbh.m, but first I'm going to open it. I mean, I can do it directly, but I'm going to open it so you can see what's in there. So I do open. I'm just finding it on my how did I copy it to the, maybe I did, not sure I did or not. Me codes, okay, here. Callbh dot, where is it? Callbh, here in the bottom, okay. So now it's going to open in an editor, and it tells you what it's going to do. You can't read it from where you are, but it's going to ask me question. The real refractive index of surrounding medium. Real refractive index of the sphere. And it says to be all done in the same way, relative to the same stuff. So we're going to go and do it together. So what I want you to do is once you're in the right directory, do callbh. At least I'm not in the right directory. Let me change my directory. Do I have it up here. Yeah, you can either run it from the top or you can call it. I'm gonna open it. MeCodes. Okay, I'm right in the right directory now. I'm gonna do call BH. Real refractive index of surrounding medium. I'll call it 1 because I'm doing everything in water. You can do it in air and call it 1.34. But I'm going to do 1. You can do it. You should get the same exact result. Real refractive index of the sphere, it should say relative to that medium. So that's the 1.05. Enter. Imaginary, maybe I can do it bigger. Let's see. No, I cannot expand it for whatever reason. Maybe somebody knows how to do it. I don't. There's a way to do view zoom. It was in the previous thing. Okay, let's. Like here, window zoom. Excellent. That's bigger. Not much bigger. Control. I tried Control plus as a Command plus. I tried. It didn't work. Control no.
You won't be able to run any preferences until you get through that code.
Sorry. Imaginary refractive index of the sphere. What am I putting there? 0.01. It spit it back to me. Radius of a sphere, I'll say, I want everything to be in microns, so I'll put 2. Because wavelength, it will want same unit as the radius in medium. So in the medium, it's going to be 0.75, because that's times 440. So 0.44. 0.44. And that's the same units as my radius of the sphere. Enter. Sorry. Here, I'll put it. Now it gives me a size parameter of 38, which is what I got. No, before I got 19. Oh, that's weird. Why do I get? Yeah, so it might be a definition here is different. It might be there's a factor of 2 just for the definition. Okay, the number of angle, because I can get for the VSF. If you give it 91, you're going to get the VSF for every degree coming out. Name of output file, I'll call it test.dat. It can be anything you want. And it's done. It's done. What?
The number of angles at 91.
91 will ensure you to have every degree you're going to get an output, but you can put whatever you want. It's gonna that's what it's going to use to generate the output. So now I have the output here, but I want to go look at my output. Here is the test.dat. I'm opening and I'm getting in Excel. In Excel, what do I get? I get in the top the all my inputs. In the bottom, I get QC as 2.7. I get for QC. Is that correct? 2.03 for QB. And 4 points, no, what am I getting? 0 points, I'm getting something very different, don't I? I'm getting 0.7, maybe I put something wrong. QC is 2.7. I got almost double in everything because my X is doubling. Let's see what mistake I made. 2.03 and 0.7. 2.03 and 0.7. So this is very different. I think I made a mistake. Let's go see what I made as a mistake. Because my X is double, and that's probably what happened. So let's run it again. 0.05, 0.01. Ready for the sphere. Everything is good. Why do I get?
91.
That's correct. It's 440. 1.01. No, for whatever reason, my X is twice what I expected it to be. Let me look at the. Sorry, guys. 2 pi times radius here. Ah, it's the radius of the sphere, and I put the diameter. It asked me for the radius, I put the diameter. Okay, back to square one. Let's run it again. Cold BH. What's the refractive index of the medium? 1.1. I did it relative to what? 1.05. 0.01. So you have to be careful about detail. Radius of the sphere, not diameter of the sphere. Radius is 1. 0.44 times 0.75. That's the wavelength in water. 91 test. What? 0.01. Test dot that. Yeah, now I got 19 for the x. It's out. The output is out. Let's open it again. Okay, finally, I got a Q of 1.62. 1.62 instead of 1.54. Not too far. For QC, for QB, I got 1.19. And I got 0.42 for QA. So I'm close. And I'm not going to calculate the A, but you can immediately see that whatever change in proportion here is going to translate. If I have a difference of 3% here, it's going to translate at 3% here. What? Yeah, if you want, we can put them E. Okay, tell me what you got. So 0.07, basically. What did you get for?
B was 0.188.
So 19.
And then C was 0.255.
2526. So overall, a change, but not a big change. You know, order 15%, something like this. What? Not a factor of 2. And among friends, if it's not a factor of 2, we're pretty happy. And look at the output. The other thing you get from this output is you can plot the phase function. So I'll just do that for you in Excel here with the output I get. Because it's always cool to get the phase function, which you cannot get from the approximation. So here it is. I'm going to data, text to column, next. It's going to be a space in between them, no tabs, finish. Okay, here they are. Actually, this is, and I'm going to now plot one versus the other. Uh-oh. Here there's no space. I'll have to. Okay. Now I have them all, and now I can. So everybody was able to run the Me code? I'm now just plotting the VSF, the phase function, sorry. Actually, this is the volume scattering function. It's not the phase function. Okay, now plot, insert, chart. What kind of chart? I like scatter charts, smart scatter. Oh, so it changes. This is the phase function. It's not the VSF. Sorry. To VSF, we have to multiply by QB. And then by the cross-section area. Let me just change the axis so it's in a logarithmic axis. Where do I do that? Format axis. We're gonna scale, display unit, logarithmic scale. Okay, here it is. And these are the famous resonances that you get if you have a very monospecific size, which is just a light bouncing back and forth inside the particle. Yay! We got a VSF. Oh, phase function, sorry. We got the phase function. That's normalized. So if you integrate under, you should get 2 pi integral of this, sine theta, d theta, the whole should get 1. Everybody's on board? Ike, you on board? You were able to plot it? Yeah. Awesome. Super. Okay, so now we go back and we continue playing. So the next exercise, let's assume we are dealing with non-absorbing raindrops. So now we do atmosphere. So James, now starts the fun. This is an example I love because I concocted it a few years ago. What can I do? I get excited about stuff like this. It's geek fun. We're dealing with rain. We're dealing with water in the air. Okay? And as you know, fog, all fog is just drops of water. But somehow when fog is in the air, you can't see anything. And when it's large drop, there's no problem seeing stuff. So let's see if me theory can explain to us what's happening there. Okay? I think it can. So, and the way I look at it is the mass-specific attenuation of water. Okay? So we have water in the air. What do you think is the index of refraction of water in air? Anybody? Any idea of water in air? What's the index of refraction? Exactly. We have 1.34. And we'll neglect absorption. So it's not absorbing at all. I put here 1.33, but it's fine. In wavelength, our eyes, photopic response, green is what we see very well. So I'm going to put lambda is going to be 0.55 micron in air. Okay? And how, so now my question is the following. How does the specific attenuation of the water in air changes as function of size? Okay, so what I want to put here is the specific, mass specific. So I have the same water in the air each time packaged to different size drops. Same amount of water in the air. What I'm asking is how does it change the attenuation in air? Okay, so C star, this is equal to, let's develop that. This is equal to, we said, we need the QC to start with. We need the cross-sectional area, pi d squared over 4. We need the concentration. But then we divide this by, this is mass specific, so mass is concentration times volume. We said 8 times the density. The density is 1,000 grams per meter cubed. Is it true? It's a kilo per liter. Per meter cube, it's one. What am I doing? It's no 1,000 gram is it's before I'm kilo 1,000 kilogram per meter cube. That's water. Okay, so I want you to plot this for particle of the following sizes. D equals, and I mean we'll write the values and then we'll plot it. Come on. Oh, I see it there. So D is 0.01. This is micron. 0.01, 0.1, 1, 10, 100, and 1,000 micron. These are all, okay? Now, none of the approximation you have there will cover all this range, so we'll do it in me. And so for that, I'll need to, so what I'm asking, first we'll calculate the beam attenuation for each size, and then we'll calculate the C star. So let's start by beam attenuation for each one particle per meter cube. That will be our, so now concentration goes out both bottom and top, so you don't have to worry about this. So let's do the QC, QC for particles. What size we have, this will be diameter. we have 0.01, 0.1, 0.01, 0.1. And each one of you doesn't, you can divide and conquer. We can, each two of you do one size, and then we'll write it on. 10, 100, and 1,000. Anybody can throw values. What's the QC that you get? For the first one, how much? 3.9 10 to the negative 6. That's for the first one, QC. 0.01 micron. And remember, it's asking for radius, so divide it by 2 when you're putting it into the Me code. What? And then we'll get from this the C star. We'll calculate what the C star should be. So you're dealing with green wavelength in air 0.55, 1.34 in air or 3.3, whichever you want. And then we're looking for C star. Sorry, 0.036. Okay, that's the next size class, 0.1. So our QCs are increasing. .0368.